Hello friends. So in today's question, in the figure, a bar of mass small m is on the smooth inclined face of the wedge of mass capital M. The inclination to the horizontal being theta, the wedge is resting on the smooth horizontal plane. Assuming the pulley to be smooth and the string is light and inextensible, find the acceleration of mass capital M or wedge M when M and small m are always in contact. So this is the figure. So we have a wedge of mass capital M having an angle of theta with the horizontal, and there is a bar of mass small m which is connected to the fixed point through the pulley P. So let us first of all draw the various forces which will be acting on the entire system. So first of all, there will be a tension T, and because of this contact, let us suppose there will be a normal of N2, and because of this contact, let us suppose there is a normal of N1. Okay. Now first of all, we are going to find out what will be the respective acceleration of both the wedge M as well as bar small m. So acceleration of wedge M and bar of mass small m. In this case, we can say, let us assume that this wedge capital M moves towards, it is going to obviously move towards in this direction by a distance x. Okay, and the inclined plane will be also going to move in a direction which is at an angle of inclination theta, and let us suppose that it moves by a distance y. So we can say that let wedge M moves in or toward right by a distance x, and this implies that bar of mass small m moves along the incline by a distance y. So in this case, there are no, can clearly see that the movement of capital M as it moves toward x with the same amount, the mass M is going to move downward. Okay, you can say that the distance covered by wedge M is equal to distance covered by bar of mass M. So from here we can say that x, this implies that x is equal to y. So if we double differentiate this equation, double differentiating, we get acceleration of capital M is equal to acceleration of small m, and we say let, as these both acceleration are same, we can say let am is equal to small am is equal to a. So they both are going to move the same acceleration. One will be moving towards right, another one will be moving downward with the acceleration a along the incline. Excuse me. Next, let's draw the free body diagram for, first of all, mass capital M. Free body diagram for wedge M. Suppose this is wedge M. So it is going to have a tension T in this direction, and there will be mg acting in downward direction. There is a normal N2 in the upward direction, and there will be normal N1 which will be at a certain angle. This is normal N1, and it will be making an angle of theta with a vertical. And next we can say we are also going to have a tension T which will at a certain angle also. Okay. So let us make this as a two coordinates. This is x and this is y, and there will be tension T which will be making angle of theta with the horizontal. Okay, this is tension T. Now we can divide this N1 into two parts. We are going to have this N1 sine of theta, and here it will be N1 cos of theta, and similarly we are going to have tension. This will be T cos of theta, and this will be T sine of theta. These are the various forces which will be. Next, as the motion is only in x direction, so we are going to ignore all the vertical components and solve only the horizontal one. Okay, and we just said that this will be moving in this direction with the acceleration of a. We can use the equation that T plus N1 sine of theta minus T cos of theta is equal to MA. And let us be equation number 1. Okay. And this is, you can say, along x-axis, along x-axis. Now similarly we can do it for the small m also. So we can see the three body diagram for bar of mass small m. So we can draw the free body diagram for mass small m, and just make sure that it is in the acting in the vertical direction. So we are going to get this as me draw into new page. Okay, it will be much more easier to get the equations also. You can see that free body diagram for bar of mass small m. So this is our inclined plane, and this is a, first of all it is going to have a mg in the downward direction, okay, and relative tension T, and we are going to have an acceleration in this direction also, and that will be given as ma. Okay. We have a normal n1 also, so this is a normal n1, and we can divide, so this will be angle theta, and so we can divide mg into two parts. We have this mg cos of theta, and this will be mg sin of theta, and similarly this will be at an angle of theta. Let me complete this one. This will be theta. So we are going to have a component of ma in the downward direction. Okay. We can call this as ma cos of theta, and there will be in upward direction, that is ma sin of theta. So we can write the equations. Let us write along x-axis, along x direction. We are going to have x and y. We have mg sin theta plus ma cos theta, and we have minus t, and we have said that it is moving in downward direction with the acceleration of a, and this will be equal to ma. Let's call this equation number 2, and next we write for along y direction. We have our n1, and we have ma sin theta, and we have minus mg cos of theta, is equal to 0. Let us call this equation number 3. Now we are going to use equation number 2 and 3. From equation 2 we are going to find out value of tension, so let us write it here. From equation 2 we get T is equal to mg sin of theta plus ma cos of theta minus ma, and from Equation 3, we get N1 is equal to mg cos of theta minus ma sin of theta. Now we are going to use equation number 1. Using equation 1, which was our, let me write it here, t plus n1 sin theta minus t cos of theta is equal to ma. We put value of t, or we can, let us combine these two things. So we can say t taken as common, so we get 1 minus cos theta plus n1 sin theta is equal to ma. Now we put value of t as well as n1. T was equal to mg sin theta plus ma cos theta minus ma, and this is 1 minus cos theta. We have plus. Now we put the value of n1. N1 was mg cos theta minus ma sin theta is equal to ma. So we are supposed to find out this acceleration a. So we open the bracket, we get this as mg sin theta into 1 minus cos theta. From here we can take a as common, so this will be plus a, and we get m cos of theta minus m to 1 minus cos of theta, plus we have mg cos of theta minus ma sin of theta is equal to ma. Now shifting the like terms to one side, okay, so we can say that mg sin theta 1 minus cos theta plus mg cos theta is equal to, taking a as common now, from here we get m cos theta minus m 1 minus cos theta, and from here we get this will be plus m sin of theta, and we can take minus here. So we can say that a will be equal to mg sin theta 1 minus cos theta plus mg cos theta divided by m sin theta minus m cos theta minus m and 1 minus cos theta. If required, we can further solve it. Not much of calculation left now. Okay. So we have a is equal to mg sin theta 1 minus cos theta, and we have plus mg cos theta, and divided by m sin theta. M sin theta minus m cos theta minus m, and we have 1 minus cos theta. First of all, we can, I think I missed something here. There was two mistakes. One was m was missing here, and another one was n1 was supposed to be multiplied by sin theta. So let me do it again. That will make it the things more clear. So we have the equation which states that t 1 minus cos theta plus n1 sin theta is equal to ma. We put value of t. So value of t is mg sin theta plus ma cos theta minus ma multiply 1 minus cos theta, and we have n1 we have mg cos theta minus ma sin theta, and this is being multiplied by sin theta, which is equal to ma. Okay. Now we open the bracket, this one. So we get this as mg sin theta plus ma cos theta minus ma, and we multiply by now cos of theta, we get mg sin theta cos theta minus ma cos square theta plus ma cos of theta, and open this one also, plus mg cos theta sin theta, and minus ma sin square theta is equal to capital M. Now this cancel out with this term, okay, and now we can solve it. We can write this as mg sin theta plus, we have ma cos theta and ma cos theta, this will be twice ma cos of theta, and we have minus ma cos square and minus ma sin square, so this will minus ma sin square theta plus cos square theta is equal to capital M. So this can be written further as mg sin theta plus twice ma cos of theta minus ma is equal to ma. Okay. I missed one thing here, that is minus ma also. So let me put it here. This will be giving me minus ma. Okay. So this will be consisting of minus ma here, yeah. So there will be minus 2ma. Now looks it correct. Next we combine the like terms. We move this as ma minus 2ma cos theta plus 2ma is equal to mg sine of theta. Now taking a as common, we have this as m, rather capital M, capital M, and taking 2ma common, so we have plus 2ma, we get cos theta minus 1 is equal to mg sine of theta. So finally we are able to solve it. Acceleration is equal to mg sine theta m plus twice ma and cos of theta minus 1. So this is our acceleration of the wedge. So you can see that this is our acceleration of the wedge of mass capital M. Thank you. There's a small error here also. I forgot to take this as minus, and this will be plus, minus, and this will be plus. Now it's complete. Sorry for the mistake. Thank you.